previous lectures, we have developed the EOF through slit microchannel under the Poisson-Boltzmann model. That means the ion distribution is assumed to be governed by the Boltzmann distribution, equilibrium Boltzmann distribution under several simplified situations. So, what we derived, if we look back to the previous problem, is the velocity at any point is governed by this relation, or this is the velocity profile within the slit microchannel, and phi, the induced electric potential due to the Debye layer charge or surface charge density, is quasi parabolic kappa y by quasi parabolic h kappa h. So, this is the situation where we have assumed a central symmetry. This is x, this is y, and both the channel have similar same zeta potential. So, that we have the EOF have a central symmetry about the line y equal to 0, and UHS is the Helmholtz-Smoluchowski, I guess correct spelling, relation or velocity, which is equal to minus epsilon E E0 zeta by mu, where zeta is the surface potential of the wall, which is dimensional in this case. In some books, zeta is referred as the non-dimensional, which is scaled by the thermal potential. Now, in the I will ask you to consider the situation where there is a combined pressure and electroosmosis driven flow in a slit channel, in a slit microchannel with surface potential as zeta, constant given surface potential as zeta. So, that means you have a pressure gradient, so a constant pressure gradient is imposed, gradient say dp dx is imposed, and also there is an electric field E0 is applied across the channel. So, that means there will be a superposition of the Poisson flow and the this EOF flow. So, this can be solved quite easily by a superposition of the pressure driven Poisson flow with the electroosmotic flow. So, one can obtain the velocity profile, etc., and all these things. So, obviously, the phi equation or the charge density charge distribution will not be affected by dp dx, because we have assumed the ions are independent, or distribution of ions are independent of the fluid flow. Because it is governed by the Boltzmann distribution. So, it is not expected that the ions and the electric potential will have an effect because of this imposed pressure gradient dP dx. So, that is what one can derive. The velocity profile only will have a effect because of this pressure gradient. Now, in some situations we may have a different zeta potential. A similar way one can derive the corresponding velocity profile distribution. So, suppose you have a situation where the zeta potential, so y equal to 0, say phi is, let the walls have different zeta potential. We are considering this situation. So, y equal to 0, you have phi equal to zeta 1, and y equal to h, you have phi equal to zeta 2. So, the same way one can obtain the solution. That means the Boyson-Boltzmann equation d2 phi dy 2 equal to 2n0 z e, if it is a jet electrolyte, if we consider, and epsilon e sine parabolic z e kbt by kbt phi. So, if you do little manipulations and all and apply this boundary condition, one can obtain the velocity profile. Velocity will be the same because the velocity conditions are remain the same, u is 0 and at both the walls. So, one can get the phi given by zeta 1 cos psi parabolic kappa y plus zeta 2 minus zeta 1 cos psi parabolic kappa h by sine parabolic kappa h into sine parabolic kappa y. I hope this is a correct expression. So, one can obtain very easily by integrating this equation with the help of this boundary condition, and similarly you have the equation for velocity, which is nothing but the relation between the viscous force and the force of the electrostatic body force. So, through that relations one can obtain the u profile as well as phi. Now, one point to be noted here is that the uy, whatever we are obtaining, is uhs into 1 minus cos psi parabolic kappa y by cos psi parabolic kh. Now, this term is tending to be 0 if kappa is many times larger than h. Kappa is nothing but the lambda inverse is the kappa inverse of the ideal thickness. So, in normal situation you have the lambda to be quite low. That means the lambda h is implies lambda h is many times less than 1. So, in that case uy basically is something like uhs, and also we have shown that the volume flow rate, average fluid velocity, these are all looks like a UHS governed by the UHS, and this is the UHS, the Smolchowski relation, that is epsilon e E0 zeta by mu. So, obviously, if I control the surface potential zeta and the E0, we get a different type of flow. So, if we have a situation where zeta is opposite to the rest of the channel, so we can have a flow reversal. So, that means here suppose I have a zeta, theoretically speaking, if I have a zeta which is less than 0 and here I have a zeta which is greater than 0 by considering some different kind of metal or putting micro electrodes on the wall. So, this will draw a flow. If this is the E0, so this will draw a flow like this, and this will draw a flow like this. Near the ideal will be of opposite direction, opposite form of the ideal. So, this is an important aspects in the electroosmotic flow, so that one can switch the electroosmotic velocity, and also it can be handled very sophisticatedly with the E0. If it is a DC, we have considered DC, it can be AC, time dependent, and all these things. So, these are the importance of the electroosmotic flow consideration. Now, we would like to find out the current density, electric current density in the slit microchannel for the fully developed situation. Electric current density in slit channel. So, again we are considering a fully developed situation. That means the conditions whatever are imposed along the two end of the channel, infinitely long channel, it is a long channel. So, wherever we are considering the flow situation is not going to affect. So, that is why this is independent of the way it is developed at the two ends. So, that is why it is referred as a fully developed situation. So, that means the gradient with respect to x is the direction, or x is the axis of the channel. So, the gradient with respect to x is considered to be negligible. Now, electric current density we have defined as F sigma Z I and the flux of the ion, or in other words, if we write in terms of number concentration. So, this is the molar flux of the ions, ith ionic species. So, summation over all kind of ions whatever we have, say n number of ionic species, and here if I write in terms of number density. So, this is becoming in Ni. Okay. So, this is the summation over all number of ionic current, ionic species, where NCI is the molar flux of the ith ionic species, and can be written as NCI is a vector. So, this is as we have derived previously, Ci u is the velocity, minus di grad Ci plus Zi di by RT, this is RT, F Ci E is the electric field. So, we have to remember every time y equal to 1 to whatever the number of ionic species. See, this is the term as we have stated before, it is due to the fluid convection. This is the molecular diffusion if you have a gradient of the ions present, and this is the electromigration of the each ionic species or each of the point charges we are considering. So, a fluid whenever we are considering the fluid flow. So, we have a volume of fluid we have taken into account. So, the net charge of that volume which is containing in the continuum is given by this Z I F C I, and so this is affected by the E, and this is the mobility d I by R T. So, mobility as we have defined before is the electrophoretic or the translational velocity of the ions per unit electric field. Now, in if I write in terms of Ni, that means the number concentration. Of course, we know that E in Ni equal to Fci. So, we have to just change over there. Now, E is the electric field, where E, the electric field, is equal to minus grad phi. Now, this phi, as we stated before, is composed of two things. One is the external electric field, another is the induced electric field. So, that means phi we have written as the external electric field. So, let us call this psi plus phi. So, psi is the electric potential due to the applied field, and phi we referred as the induced electric potential. Induced because induced by the surface charge, induced electric potential. Now, for the sake of simplicity, what we have done is we have taken the applied electric field is along the x direction. So, psi can be minus E0 x, and phi we have taken as a function, and phi is a function of y as del phi, del x, and all these things gradients are 0 due as the equal 0, as we have considered since we can say, as we have considered a fully developed situation. Fully developed case. That means that is the EOF is unperturbed by the inlet or and outlet boundary conditions. This is a kind of repetitions of whatever we have discussed previously. Now, so the current density is governed by this way. So, it is a vector. So, we now want to take the average current density per unit width of the channel. So, this is we define as I. So, this will be minus h to h I x dy, because x is the component along which the current is flowing, and dy is the area. So, this is the I x dy. So, this is basically we have to find out. So, per unit width. So, if I have a width as known to be w, so if I multiply, so we get the current density of the net current density. Now, if I write these I x from the expression of I, what I get is, so I can be written as minus h to h. I x means we have E u. So, we are summing over all the ionic species Z n I minus E square by k b t, which is E by k b t is nothing R t by F, and this is del phi del x into sigma zi square di ni dy. As del ni del x equal to 0. So, those terms are neglected, and we have already, and del phi del x is minus E0 x. So, now if I substitute there, so what I get is, so one term is due to the this is involved the fluid flow, and another term is the diffusion terms. Now, we can, okay, now since we have to write this E0 x del phi del x, so that becomes E u sigma zi ni plus E square by kbt. So, this is becoming, I can write as f square by RT E0 sigma zi square di ci. So, we have now again, so if we have switched over here, so I think we should switch over here also. So, this is basically minus h to h, and this we can write as f u sigma zi ci plus f square by RT E0 sigma zi square di ci. So, this term is called the convection current. So, let us call the term as IU, and this is the conduction current. So, the first term due to the fluid convection. Now, one important thing is here, if ZICI is 0, so that means it is electrically neutral. So, whether you have a convection, fluid convection or not, it does not matter. I becomes independent of the fluid velocity. The fluid convection referred as convection current IU, and the second term are due to the conduction is called the, or referred as the conduction current. For a electrically neutral electrolyte, neutral situation, I is independent of fluid convection. Okay. Now, if we now substitute we consider the Boltzmann distributions and substitute the CIs and all whatever we have derived previously and get the expression for I. So, first of all, we have already defined the electrical conductivity as nu as f square by RT into sigma Zi square di Ci. Now, if I take the diffusivity or SEM d1 equal to d2 say equal to d or SEM in a binary symmetric electrolyte, with say let us take for simplicity Z1 equal to Z minus Z2 equal to 1. So, what I find is nu equal to nothing but 2f square. This is we are taking as the bulk, Ci0 is the bulk concentration. So, 2f square by RT and dC0. So, this is the reference conductivity. Now, we define nu bar equal to that other term f square by RT sigma Zi di Zi square into this term whatever we have minus h by h and Ci dy, and let us take as 1 by 2h because nu bar is the average, as the define nu bar as the average conductivity, because the conductivity changes along the h because it is depending on Ci, but here this is the scale one. So, with reference to the equilibrium or a bulk case where you have a electroneutrality is established. So, we can write as the Ci0 is the reference value. So, if I define this way, so now if I do the integration and if we put back with that, what I get is 2h nu bar and you have the u Zi Ci. So, now u I substitute there. So, what you get here is E0 epsilon E square by mu minus h to h phi minus zeta into d2 phi dy 2 dy. This kind of situation we get by substituting the u is, as you remember, u equal to E0 epsilon E by mu phi minus zeta, and also we know this rho e, which is basically f sigma Zi Ci is nothing but minus epsilon E d2 phi dy 2. So, these are the terms, these are the substitution we have made over here. So, this governs the bulk this is the bulk ionic conductivity and this is the average current density through this slit microchannel. Now, we will continue in the next class on deriving this I.